Good morning, everyone. I'm going to talk to you today about identifying causal effects from a combination of surrogate experiments. This work is joined with Sang-Hak Lee, who's the first author, but unfortunately, due to visa issues, he could not be here today. So I'm the second author there. I'm going to be presenting it, and with Professor Elias Barenboim. Okay, so one of the main tasks in many empirical sciences, engineering, businesses is to identify causal effects. We like causal relationships because they are good for constructing explanations and predicting the effect of interventions that we have never experienced before in new settings. Controlled experimentation is one of the main tools to achieve this. However, it's not always possible to perform an experiment to find causal effects. Among other reasons, it could be unethical to perform an experiment, or it could be technically impossible. Think, for example, to randomize the cholesterol level of a patient. We cannot just decide some level and set to a fixed value, or it could be very costly to perform. In this paper, we would like to understand what are the conditions that allow us to extrapolate a set of observational and experimental distributions to find a causal effect. In order to do this, we resort to the framework of structural causal models. Here, we assume that the phenomena under investigation can be modeled using a set of observed variables, B, that will take their value according to deterministic functions f that could take as input other observed variables and unobserved variables, and the randomness of the model comes from a distribution over these unobservable variables, u. In general, we assume that this model is not known to the investigator, but we do assume that a causal diagram, which represents these functional relationships among the observed variables, is known, and it encodes these constraints. The same kind of model also implies or induces a set of distributions, not only an observable distribution, such as P over all the variables in the set B, but also experimental distributions where different observed variables have been controlled. Here, this notation P sub x1 means that x1 has been controlled and that we are observing the set of variables B. In general, we could say that the problem of causal identification takes as input these three elements to the left. First, we have a query, which is the effect that we want to figure out. We will denote this as P sub x of y, meaning the effect of fixing x to some specific constant. What is the behavior that we will see on y? This is the same as P of y given to x, if you are familiar with this notation. Also, as I mentioned before, there's a causal diagram that is encoding the assumptions that we're making about the underlying unknown causal model. And we have data that usually comes in the form of observational distribution, but we will generalize this a little bit. So based on the current knowledge about the phenomena, which is represented in the graph, based on the available data that comes in the form of a probabilistic distribution, is the research question, in this case the causal effect, identifiable? This is the question we want to answer when we are doing causal identification. The answer could be yes or no. Whenever the answer is yes, we want a formula that maps this effect of interest to a function of the observed quantities. Whenever the answer is no, we would like some evidence that in fact we cannot distinguish this causal effect from the assumptions and available data that we have. In this paper, we generalize this. We don't consider that observational distribution is the input or the only input, but it could be a combination of data that could come from other identification tasks or randomized clinical trials, or also including an observational distribution. Just to motivate, let me give you an example on drug-to-drug interactions. Consider this causal diagram. Here, variable y has the meaning of the development of cardiovascular disease for a patient. B is blood pressure. X1 has to do with treatment for hypertension, and X2 is treatment for diabetes. we could have different studies. Here to the right, we could have one study where we randomized x1 and we observed the effect on the variables b. This is one trial. We could have a different trial where we studied the effect of x2. So we have independent studies where we know the effect of these drugs, but we would like to answer the question of how both treatments applied simultaneously what effect will that have on the variable y. So the goal is to assess what is the effect of prescribing both treatments based on independent information that we have here. For this particular causal model, this can be achieved by combining these quantities that are observed or available to the right. We can combine them and obtain the effect to the left, and this is guaranteed by the assumptions that this causal model is implying. A similar model could have some confounding between blood pressure and anti-diabetic drugs. Maybe we found that there is a strong correlation between them and that there are variables that affect both, so we can add this assumption with this arrow here, and the answer is still positive, meaning we can still find a mapping between these two studies and the causal effect of interest. However, other modifications, for instance in figure C, if we have confounding or latent confounding between B and Y, then the answer will be no. Even if you have both studies, it is not possible to uniquely identify this effect for this case. So it is not obvious when the answer is yes or no, and that's why it's important to study these kind of situations. Let me give you a second example that arises from multivariate testing, which is a generalization of A/B testing, where we don't have only one treatment randomized at the same time. Suppose that x1 and x2 are features of some product. It could be for advertisement, the format, the font, the position, different features, and we have different outcomes. Could be revenue, click-through rate. Let's say that for a company, different teams do experiments with these variables simultaneously. So here we have one data set where we observe the joint effect of some features on these variables at the same time, but we would like to distinguish what is the individual effect of particular treatments based on this joint information that we have. For this particular graph, this can be achieved for both the case of what is the effect of x1 on y1, just by this equality, and similar for x2 on y2. This is the case for this particular graph, but for other slightly different graphs where we have these new arrows, the answer will be no. Even if you have this controlled experiment for both treatments at the same time, it is not possible to distinguish the individual effect of the treatments for these two diagrams. We would like to formalize this problem, and we call that g-identifiability. So again, we have sets of variables x and y that correspond to the treatment and the outcomes. We have a collection of sets of variables called z here that describes different experimental conditions. So each one of those experimental conditions describes a distribution, meaning we could have z1 randomized, and then c1 and c2 randomized, and then c4 randomized, and we can just specify what are those distributions that we have. And again, we have a causal diagram encoding our assumptions. Then we say that a query p sub x of y is g-identifiable from this set of experiments and the diagram if it can be uniquely computable from the corresponding distributions for these experimental conditions in every model that satisfies the assumptions in G. Just to ground this and relate it to previous work, starting from Pearl 1995 and going through complete results from Spitzer, Huang and Valtorta, and the work from Jin Tian, we have that from observational distributions, we want to identify what is the causal effect. So from PV and the assumptions in a graph, we want to find what is the effect of X and Y. This is the most traditional identification kind of task. We have a generalization of that, where we also incorporate experimental distributions. So we assume that there is a set Z, such that we have every experimental combination due to Z. So if Z is Z1 and C2, we assume that we have Z1 and Z2 jointly randomized, only Z2, only Z1, and that we also have none, meaning the observational distribution. This constraint could be a little bit strong in practice to assume that we have every possible combination of experiments. There is a slightly generalization of that, but still for our setting, we make this completely arbitrary. So we could have any combination of experiments for this setting, and we again want to find what is the causal effect of some particular set X on Y. This is just a picture of these problems that I just mentioned. So our setting is more general and subsumes the others. We would like to first design an algorithm to solve this problem. By contrasting these to previous solutions to these other problems I mentioned, one first challenge is that observational distributions could be the target of our study. If you don't have observational distribution as an input and you just have a bunch of experimental distributions, a valid question is, can we recover some observational regime? Can we do prediction on this model even though we don't have natural observations of the system? A second challenge is that we, as I said before, don't have every possible subset of experiments, just some particular experiments. In order to do this, the general strategy, and I will go a little bit more into detail of this, is that given a query, p sub x of y, we want to modify and divide this query into smaller pieces that can be systematically handled. And each one of these pieces or subqueries, we will try to identify it from at least one of the available distributions. So if we fail to identify any particular subquery, it means that none of the distributions that we have available are enough to indistinguishably give us that piece of information. This is how the algorithm looks like. I'll not go into the details, but I'll just mention that every step is just checking or modifying the query by removing unnecessary variables, adding some more variables to the intervention if that's convenient, factorizing the query into smaller pieces. And each one of those pieces goes to a subroutine that is in charge of, given a particular distribution that we may be able to use, try to identify the causal effect on that specific distribution. To give you an intuition of how it works, let me recall this example from before. So again, given a causal query, first the algorithm will check if it can remove some variables from the graph that are not relevant to the particular query, and we'll try to add more variables to the intervention if that's helpful. In this case, that is simple. The query remains the same up to this point. Later, we try to factorize this query into smaller pieces. So first thing the algorithm will do is to express or to introduce variable b here, and then we can use the constraints implied by the graph to break these into two terms. And then we can try to modify each one of these subqueries. Now we divide and conquer. And later, we will try to identify each one of these two pieces from the available distributions. So the first term, for instance, is ready because we are assuming that we have experiments on x1. So p sub x1 of b, it's available from the input. We still need to identify the second term at this step. And here we end up with the causal effect expressed as a formula that involves two quantities that we observe or that we have available from our input. So this is what happens when it is identifiable. We get a formula. What happens when it is not g-identifiable? The definition before was that it is g-identifiable if the effect is uniquely computable. So to prove that it is not g-identifiable, we need to show at least two models that will match the same graph, that will match in every one of the experimental distributions that we are considering as input. However, they will give different causal effects of interest. So they match in all our input, however, the target effect is different. So it's not uniquely computable. Then it is not g-identifiable. These are three instances. The first two are from the examples I gave you before. Here we can have a set of experiments. Again, our target is the effect of x and y. And we can show that we can come up with two different models for each one of these graphs that will match in every input, but will give a different causal effect as output. So is there a pattern here? graphically that we can exploit in order to characterize when this is non-g-identifiable. So we define a graphical structure called Thicket, and we prove that whenever this structure is present in the graph for a particular query, it will imply that the effect is non-g-identifiable. Again, we prove this by explicitly constructing models that will match in the input but will differ in the target effect. And we also show that whenever our algorithm fails, we can guarantee the existence of such a structure in the graph. And this again will imply that the query is non-g-identifiable. So whenever the algorithm fails, it is because the query is non-identifiable, making it complete. Again, just to show you what a ticket looks like with an example, consider again this graph that we have here. Notice that I added the confounding between B and Y. That is the part that made it non-g-identifiable compared to the original example. And again, our target is to find the effect of x1 and x2 jointly on the variable y. And we have experiments on x1 and x2. Thicket is made of smaller structures that we call hedgelets. So these structures correspond to these subqueries in which we can decompose the effect. So a first one of those structures is this one between x2 and y. There is some latent confounding here that make it impossible to find the effect of x2 on y for certain inputs. So there is this first hedgelet here. There is a second hedgelet made by these three variables. When we superimpose those two elements, we can satisfy the formal definition of Thicket that we prove in the paper. I'll not go into the full detail of that here, but if you feel curious, I think it's well explained in the paper, and I can help you with any question you have there. The point here is that whenever we can find this structure in the graph, we can get the result that the query is non-g-identifiable. Now to conclude, I will mention again that in the paper we are given a complete graphical condition that corresponds to the Thicket that allow us to determine if a given query based on this experimental collection of experiments and the target effect is g-identifiable or not based on the assumptions in the graph. We give a sound and complete algorithm that exploits this characterization, and whenever the answer is yes for the g-identifiability problem, we'll give a formula that relates the available input to the target query. And whenever the answer is no, we'll provide some evidence in the form of this graphical structure that allow us to construct this explicit and formal counterexample that shows non-g-identifiability. And we hope that these results will allow for causal inference settings in broader experimental conditions that could be closer to what we could find in reality. These are some references that we use, and thank you very much.